smaller parts. My flat earth people, shush. The components are the smaller pieces of the whole, right? My components are the smaller pieces of the whole. So the whole vector, despicable me, has two things. The whole vector has two things. What does it have? Direction. But that can get really hard to solve with, and I'll show you when we get to word problems how that gets difficult. But even though he said direction and magnitude, he was totally right. That's the whole thing with two pieces. Inside the vector, we can break it down a little bit into components. Those are the side carets. There's a horizontal change and a vertical change which says, hey, how far over and how far down, because remember this guy had to go from R to S, you have the arrow pointed that way. So we need a positive horizontal and a negative vertical in order to get to that point if we were to actually express him. So we have the side carets, we have two quantities, and they represent the components for a vector. How to go from the tail to the head, how to go from the initial to the final. So then we were just starting to say, okay, what if a problem asks you to multiply a vector by a scalar? That's a snazzy word for a coefficient. Not another vector, but by just one number, one constant. You guys remember, because remember the board wasn't working so well, it was kind of messy and nasty. So I erased it so we could write it prettier today. But do you remember how I told you to multiply a vector by a scalar? Yeah, C times both of them, right? And let me show you today, now that the board is working a little bit better, what that's going to look like down here. So let's say this guy is vector V. And I could say this vector has a certain length, magnitude, and a certain direction, a certain... Okay? Hold on, we didn't do the picture on Friday. You guys should all be writing the picture down. Joel notes should be open. Let's go. Let's go, let's go. If for any reason, I know in calculus I have a few kids that are like, I'd rather just listen and write down at home, just come talk to me and be like, hey, that's how my brain's working. Look at my notes. I truly do read them every single night at home with the video. That's fine. Just need to tell me so that I know. Otherwise, I think you're just spacing out and deciding not to be committed, which I would then say, well, why are you here? Okay? But some people, both my calculus classes would rather just sit and listen, and that's how they learn best. So just come talk to me if that's how you learn best. That's fine. Now, if I multiply the horizontal, which I can label down here, if I multiply the horizontal, which would be the V1, that's this measure right there, and the vertical, which would be a length of V2. If I multiply both of them by C, let's say C was, I don't know, let's do an example. Let's say they were to ask me, hey, why don't you find 3, ooh, let's make it interesting. Oh no, stupid. 3 times vector V. What do you guys think is going to happen to vector V? Please multiply by 3. Yep. It's going to get longer. It's going to get bigger. And if we think about this, well, that's going to be 3 times V1 and 3 times V2. So what exactly is going to get 3 times bigger? Everything. The horizontal component isn't just going to be 1 unit. It's going to be 3. It's going to be 3 times as long. V2 isn't just going to be 1. It's going to be 1, 2, 3 times as high. So if I make this bottom one 3 times V1, and if I make this vertical one 3 times V2, what's going to happen to the horizontal one? Yeah. It's going to be 3 times as long. Does that make sense, guys?
Yeah.
It's kind of like similar triangles. We're just multiplying the whole triangle by 3. Now, what if, let's just make it exciting, what if I was to put a negative in there? No big deal, right? Just put a negative. Just put a negative. But I wonder what a negative means for vectors. How do you think I can make the vector be opposite? Reverse the direction. Reverse the direction. So instead of the arrow coming up here, where's the arrow going to go?
Down there, line 4.
It's going the exact opposite direction. So whenever you have a negative that's being multiplied, it switches the direction. The 3 made it 3 times longer, and the negative said, now you're going the opposite way. Does that kind of make sense? Negative is an opposite direction. Chris?
So does that just apply to V1 and V2 also, or they just like it?
Well, right now, V1 and V2 are literally just lengths. That's why there's no arrows above them. They're just numeric quantities that say how far and how far. We're soon, in another notation, going to be able to make them vectors, so they'll have their own arrows, and then we would switch the arrows on them. But technically, right now, they're just numeric lengths. They're just distances. They're not actual vectors with their own direction. Okay. And the positive negative kind of has you going the right way, but yeah. Remember how the math went when we were adding vectors? How'd the math go?
Oh, U1 plus E1.
Good. Combine the horizontals and then combine the verticals. So it's literally just going to be, hey, let's add the first numbers. Let's add the second numbers. Once again, no vector arrows above them because they're just numeric quantities, but the U and the V need the little arrows. Now, you guys actually kind of got an introduction to this when we were doing the roller coaster stuff. But I didn't actually write them down. It'd be way too hard to write down. But let me go ahead and take V. Let's move him over here. We can call this one, oh, we already called him V. Sorry, the purple one's V. Okay, this one's U. Imagine these are the two vectors acting on the roller coaster car. We saw that at the beginning of the chapter, right? Or beginning of the section. And we had one car, and then we had these different forces acting on it in one instant. But then remember, next to the picture, they rearranged everything to be able to show the net force, the resultant force. How did they rearrange it? Or how did they draw that third vector? Yeah, how is it, AJ, louder?
Oh, adding both together.
Yeah, but how did they do that? Can we go back and look at the picture real quick? You guys know what I mean, right?
Yeah.
All the different little roller coaster cars. And so we see the vectors working on the actual little people in the car. But then I said, like, oh, hey, look, off to the side, they're putting them together and seeing the net force. Putting them together, seeing the net force, putting them together. And remember, I was asking you guys, what's the common way, now putting them together, addition of two vectors. Okay, putting them together. But there was a very specific way that the net force was always drawn. Do you remember what that was? Okay, look at it now. What was the very specific way the net force was always drawn? Think about the picture that we have. Think about what you see. Did they just connect the two? Connect the two? Connect the two? Yeah. Head to tail. They had to have the vectors working together. Because right now, they're coming from the same object, but they're going in two totally different directions. Even if they're going in similar-ish, I don't know if that's similar-ish. Similar-ish? Well, those ones are similar. But even if they're going in similar directions, they're still originating from the same source, but then going off on their own. We need them to be working together in a sense. Even if the direction is different, even if the magnitudes are different, we need to put them together. And the way to put them together is to say, hey, initial to terminal, I need the gravity to terminate in the initial of the normal, and then I can flow, in a sense, flow through the two and say, oh, so from the very beginning to the very end, what's the result? Same thing here. Right now, they're originating from the same source, going off in their own little ways, their own little directions. I need to say, no. I need to see what you guys are doing all together. And to do that, even though this one's blue and then green, and that one was green and then blue, it doesn't matter. I just need to go from the very beginning of one and have that join up with the beginning of the next, and then say, okay, so what's the overall effect? What's the net force? What's resulting from you two both being at work in this model? Does that kind of make sense? So when I just have them going off on their own, I can't tell what they're doing together. So to put them together, I need to be able to flow through, which means the head of one needs to match up to the tail of the other, and the resultant or the net goes from the very beginning to the very end.
I was going to say, is it the sum?
Yeah. So the net is the sum. And so when I put them together in this way, the resultant, or from the very beginning, the initial tail to the final head, that is the sum. So then over here, I made that That was before we even started the section. I said to get the net force, we have to take the two and add them together. So let's go to that picture. Because the math is easy. If we have the components, put them together, no big deal. The picture is a little bit harder. Because should I just connect the two? No. They're going off in their own direction, Leo. Hand down. Put down. Perfect. Hand down, just all the way. Too much temptation. So we have them going off in their own direction. I need them to go together. I'm allowed to shift vectors to be wherever I want them to be. So I could either move V down, which is totally legal. I could move V down. I could shift him down. And I could connect if I wanted to. I could connect from my resultant or from my sum from the tail of V to the head of the other. That's one way. Or the other way is I could have left V exactly where he was, and I could have moved U up. Oh, not you. You. No, still not you. You? Okay, I give up. Let's do the mouse. He's a little more precise. Move this guy up. This guy up. Okay, and if I shift him up, don't I still need to connect from head to tail? A question. What do you think's going to be, well, I mean, I drew them fairly approximate. What's true about these two guys?
They're the exact same.
They're the exact same. They're in different places, but they're equal vectors. Either one's going to be the sum. I can even be I can even be a little bit snazzier. What if I had kept U exactly where I wanted him to be? And what if I had this guy going way out here somewhere? It'd still work. No matter how you add, whether it's U plus V or V plus U, whether you shift one or shift the other, you're still going to end up with the exact same resultant, which is the same thing as the sum. The exact same, I'll just leave one of them. The exact same resultant or the exact same sum. So we just need to end up putting our U and V together. And once we do, we can say U plus V is equal to this final force, which we could call, they sometimes call it the resultant vector, because it's the result of putting the two together, or the three together, or the four together, or the five together. It can also be called the net force, which is like the overall effect. We talked about net profit, etc., or the net worth of a company on Shark Tank, etc. For the resultant, we have the net. And then just mathematically, we call it the vector sum. Those are all three words to describe the same.
U plus V seems longer than the results of the line.
The distance is yes. But remember, let's think of it this way. We're going to see a word problem a little bit later, how you have a plane that's flying. And that plane that's flying, do you have, like, in the plane itself, do you have, through the engine, or the engines, I should say, do you have, like, a certain force that's propelling the plane forward? Yes. Trying to push it at a certain speed. However, if that certain speed was, and off the top of my head, I don't remember what, does anybody know how fast planes go? Let's say 200 miles per hour. I'm just throwing one out there. 200 miles per hour, the plane's going. Does that mean in 1 hour you will have gone exactly 200 miles?
No.
Why not? Air, there's wind, right? And hopefully it doesn't like run into a seagull. But anyway, wind. Okay? Wind. So if the wind is, have you guys ever heard that as you're flying in the plane? Right? If the wind is going with you, let's just do it that way. If the wind is going with you, if you're going with the wind, what's going to happen? You're going to get there quicker. Have you ever had like, you're going to arrive at this time and you get there faster? So if the wind is going with you, it's going to push you faster. So then you have the engine trying to go here and the wind trying to go here. You can literally just take, if you knew it, if it's exactly with the plane, which is very rare because the plane has a different route. But anyway, if the wind was exactly with the plane the whole time, just add the two together, literally. How fast are we trying to go? How fast is the wind blowing? Perfect. That's when we'll get there. That only happens in one situation, where you can literally just add the two together. When they're perfectly with each other, the resultant will be the exact same as the two added together. But as soon as you say, I'm trying to head this way, and the wind is pushing this way, right? Then you can't just add the two together because they're going to detract from each other. Now, if the wind was going perfectly against, we'd subtract the two. Because it'd be addition of a negative. Does that make sense? But as long as as soon as there's an angle to the vectors, then it's going to be in some ways adding and in some ways subtracting. For instance, these are not great examples. For instance, these two, if I was to take their horizontal and vertical components, that's why we usually go components. This one's going to the right and up, true. This one's going straight down. Think of this one. This one's going to the right and up, and this one's going straight down. The straight down is working against the straight up. But the right is not really being added or subtracted from. So the idea is we would do the components. This one would be a 0 horizontal plus the positive horizontal. So 0 plus that. Okay, this guy wins horizontally. He's the only one that's even moving horizontally. But this, I'm going to take the vertical and the negative vertical and then add the two together. But then overall, you're going to have a diagonal that's going to have to take both into consideration. Does that make sense? Okay, good question. Okay. So now we have an example. And there's actually numbers. I'm not going to make you guys sketch it. We'll do that all together, but can you just do the math? Now pause, hold on. Some of you have lost track a little bit. Every time you see a bold letter, what do we have to do then? Okay, good. It's a vector, right? That makes sense? It's a little vector error. Handwritten notation. I don't put vectors above the 2 or the 1 or the 1 or the 3, the 2 or the 3. They're just scalars. They're just new quantities. I'm going to go ahead and sketch U and sketch V. If you guys want, you can go straight to the math and solve for A and B and C. Literally, the math is that easy. And that's why I thought you could get through like 35-ish in homework. Because they gave you the numeric quantities. Now, sketching would be hard. But the math is easy as long as they're in the components. You guys see why I drew the vectors that I drew? He's U because he went to the right 2 and up 1, right? And then he's V because it went to the right 1 and up 3. Okay. So this is like two forces originating from the same source. Or maybe not originating, but acting on the same source. Maybe a better way of putting that. Now, mathematically, if I wanted to add these two together, it's so easy because what would my U plus V end up equaling?
3.
Yeah, 3 comma 4. Super easy. Now, pause. What would that picture look like? Wouldn't I have to take my U and take my V and say, couldn't I technically say, wait, 3, 4, couldn't I just graph that and say, okay, 1-ish, 2-ish, 3-ish, 1-ish, 2-ish, 3-ish, 4-ish. Couldn't I just draw my 3, 4 and say, hey, that's my U plus V? Yes. But do you see? No. Do you see why it's your u plus v? What would I do with that green one to make this make sense?
Yeah, bam.
Bam! But could you literally just graph 3, 4? That's why components are nice. You don't have to have all the triangles and all the relationships and know all the angles and the sides. If you know the components, just add them together and say, sweet, there's the answer. How? I don't know, but there it is. But does it make sense how it could be u plus v? Hopefully the answer is yes. Yeah.
Draw a parallelogram.
Yeah, with the original, I just shifted them over, but yeah, you could go ahead and have this guy be, and then connect. And be the diagonal. Yeah. Okay, how about u minus v? Ooh, subtraction is the same thing as addition of a negative. Oh. Now the math is easy. What would the math be? 1 and... How does that work, starting from u and v? Well, I could graph it. It's 1, negative 2, no big deal. Let's see if that's 2-ish, and that must have been 1-ish. Negative 2, well, that's going to be that distance down. I don't even need to figure out the geometry as to why. It's 1, negative 2, it's right there. But how could this make sense? Nick just brought up the idea that we can make a parallelogram. It's a horrible parallelogram. Anyway, we could make a parallelogram. We make it a little bit prettier real fast. That might help us out just a little bit on this one. Because, there we go. If we made a parallelogram with the first one, kept the original vector v, I was like, oh, hey, let's go ahead and make a parallelogram. Then we can have that diagonal be the resultant. So we could use that. We could keep this guy and say, hey, let's shift him down, keep that guy there. But wait a minute, that doesn't make sense. We can't add vectors like that. We can't have them going together and then like connecting the tails. That's weird. So I have to switch the sign of v. Because v has become its opposite, right?
Yes.
So I wouldn't bring down the original v. What I would bring down would be this guy. Oops, undo. I don't want both of them. But flipped, right?
Yes.
And as soon as I flip his direction, because it's a subtraction or a minus, does that make sense? Yeah, it's perfect. The components, the math is easy. The picture's a little bit harder. If you didn't have the components, let's just say to find this vector, you'd have to basically figure out the magnitudes and directions of each, do this translating, use properties of parallel lines and transversals, and alternate interior angles, same side interior angles, and then try to solve the triangle using side, angle, side, and law of cosines. It would work, but that was so much easier. You guys hopefully have the math of the last one, and we're going to talk about it as soon as I answer Jacob's question. Go.
Does it matter which one you switch to?
No, because remember, if we had switched the, well, wait, switched? Yeah. Because this u has to stay positive, because I'm subtracting the v, so it's addition of the negative v. Just make subtraction, you can't do a minus b is b minus a, that doesn't work. So I have to keep the negative with the v. But I could have switched the direction right here, and then I could have connected tail to head, and it would be the exact same guy, just in a different place. Does that make sense? So I didn't have to move him. I could have just switched him right there and then connected because it would have been legal and it would have been the same thing, just different location. Okay. Okay, last one. What do you guys get for the math? Okay, sorry. 1, negative 7? Because you would have needed to multiply 2 times both of these, right? 2u would have ended up being 4, 2 minus 3v. We'll have to do it all mental math, and that'd be 3, 9. And then 4 minus 3 is 1, 2 minus 9 is negative 7. Oh man, how does that work? Well, hold on, first of all. Don't we need the u to be twice as long and the v to be 3 times as long? Okay, so in order to accomplish that, I'm going to use my snazzy copy-paste thing. Okay. Couldn't I, in a sense, just clone it a couple times? right? This guy needs to be twice as long, so let's go ahead and just make him twice as long. Does that make sense?
Yeah.
Okay, now he's twice as long, the whole thing. This guy needs 3 times as long, so let me go ahead and get 3 of them. Now hold on, wait a minute though. Isn't there a negative? Ooh, who's the negative? This guy, right? The negative needs to go with the V because it'd be plus and negative, plus and negative. So I could go ahead and, let me go ahead and clone this or group that guy together too. I could go ahead and just graph the 1, negative 7. No big deal, right? 1 would be half of 2-ish. There he is. Negative 7. Let's see. If that's 3, that'd be negative 3, negative 6, negative 9. Cut that in thirds. Maybe about there-ish, right? Approximately. Okay. So I could say 1, negative 7. Does this make sense? When we have to switch that guy's direction? And when we switch that guy's direction, he would be headed the opposite direction? Make him parallel? Does it match up? You can't quite tell. My 7 was a little off. But is that roughly right? Yeah. So, vector diagrams is a snazzy way of talking about actually doing it geometrically, as far as using magnitudes and directions to show what the actual picture is and where the overall resultant force is, etc. But the components make things so much easier. But one more time, are we always given components? And the answer is no. But we can always make them if we want to. You don't have to write this down. This is basically saying vectors in many, many, many ways behave like numbers. U plus V, V plus U. You guys saw me like moving the blue, then moving the green. It ended up being the same result, just maybe in a different place. If I add 0, it'll stay the same. I can do 2 times 3U to be 6U, same thing. We can bring that constant into both separately, or we can add and then do a constant. So a lot of the properties are the same. What I want you to see is there's one thing that's very much missing from this page. And that one thing is, great, we can add vectors. We can even subtract because it's adding negatives. We can subtract by adding negatives. We can do all these associative properties. We can do all this multiplication by scalars or by numbers. The one thing that's missing is what do we do when we have 2 vectors multiplied together? Is that there at all? Because it needs its very own section, because it is something totally different than what you would imagine. So all of the picture stuff that you've been seeing, adding forces, subtracting forces, we can make sense of in like the different vector diagrams that we've been doing. This is largely absent for a very important reason. We need our own section to talk about what we would call the dot product of 2 vectors. I just want to let you guys know, vectors act very, very normal when adding, when subtracting, when multiplying by constants. They get very, very weird when we start multiplying them. But good thing is, it's not today. That's not today, so let's come back. Who was it? Chris, was it you that we were talking about the components not having vector arrows?
Yes.
Okay. This is a type of notation with an I and with a J where we can start talking about the components, the horizontal, vertical, having their own little directions. So, we'll start off with the vector V. It's actually the next page where I give you the name for the notation. It's called technically writing vectors as linear combinations. It's a snazzy word for it. Components are the little side characters. Just give me 2 numbers. They'll get me from the end to the beginning, sweet. Linear combinations say let's not just define the components with distances, let's also give them their own little vector directions as well. So we could talk about this vector as 7 and 5. No big deal. Vector V. We can talk about him as having magnitude and direction by Pythagorean and tangent inverse, finding angles. And that 7, up to this point, that component form literally just says 7 over 5 up, from tail to head. So go positive 7 to the right 7, go up 5, done. Here's kind of the struggle though. Whenever we're being given component form, or even linear combination form, to be honest, pretty much all of these say we need to start from 0, 0. It's a little bit of a dilemma. Not a huge one, because we can move the vectors and be like, whatever, we just need to keep everything around 0, 0. Okay, fine. But even though it could happen many different places, typically the 7, 5 just tells us, let's start from 0, 0. From 0, 0, let's move 7, let's move 5. But we can go ahead and put arrows, put directions on this horizontal and on the vertical, using these little guys named I and J. I'll show you how we use them in just a second. Right now, it's just define who is I and who is J. I with an arrow on top, or a bold letter in your book. It's not the imaginary number. Imaginary numbers don't have vector arrows. It's another use of I. I is used a lot in math. Not tons and tons, but it's used multiple times. It's not always referring to imaginary number. I can find or look at the context. Ooh, Bible class now. Context. So important anywhere we want to get the context of it. So this one, little vector arrow. Ooh, something to do with vectors. I is the unit vector in the horizontal position. J is the unit vector in the vertical position. I put my little tails on my eyes, that way you guys don't think they're ones. I don't really put the dots on either, because I'm like, why put a dot and then an arrow? That's why you just put an arrow. Anyway, I is the unit vector in the horizontal position who's going to have the components of 1, 0. And J is going to have the components of 0, 1. So they both have a length of 1. And they're just talking about vectors horizontally and vertically. And if we want them to be, say, 7 and 5, all we have to do is say, all right, well, if I is 1, I need it 7 times that for this guy. So let's make this 7 times I. And let's make this 5 times J. And all of a sudden, I have vectors to go along with those lengths. And so I don't just have distances, I also have directions. And how we write that, or how we write that is, hey, we can make V written as a little vector sum. This vector sum we're going to define on the next page. Let me try to show you both pages just to bring the two together. It's called a linear combination. So linear combinations. Let me try to switch the lights. When that one's dark, I feel like you can see a little better. Linear combination. Snazzy term. A snazzy way of saying, hey, let's write a vector not just in its components, not just the how far, but an actual little vector sum to literally break it down and say, hey, it's this little horizontal vector, well, the little one times 7. So 7i is the horizontal vector, 5j is the vertical vector. The meaning is super similar. It's really not that different. I just want you guys to be familiar with both of the different ways of writing. Component form, linear combination form. So if we apply what we just saw to this new example, all right, we have a new vector. His name is W. First of all, let's go put little vector arrows on everybody. We have our vector W. He has components of 4, negative 5. Well, if his components are 4, negative 5, how would, or what would his linear combination be? Yeah, a little bit louder. 4 vector I, right? You could do minus 5j, or you could do plus a negative 5j. Does that make sense? Same thing? You could do minus 5j, or you could do plus a negative 5j. Okay, I got distracted and meant to turn this up, and I just started going on vectors. You guys, I need to catch up. That'll get too hot. So it still has the 4, still has the negative, still has the 5, still has a horizontal meaning and a vertical meaning, just doesn't have side carets. It's like a little baby vector equation, a little baby vector expression for what's going on. And the basic operations, you guys can see on the notes, it works the same way, which means if you need to add, just add the horizontal components. Just now they're i's and j's. And then the vertical components as well. If you subtract, do the same thing. If you multiply by a scalar, do the same thing. So what do you guys think we would do in order to find 2 times vector v? Now hold on, pause. And notation, those should be vectors. That's a vector, he's a vector, he's a vector, he's a vector, I's a vector, J's a vector, E's a vector. Okay, anyway. How are we going to double v? Find v, find each of his pieces in the linear combination, and say, well, if I'm doubling him, what's going to happen to 3i? What's going to happen to my negative 2j? And it's still negative because I've done nothing to change the direction. Just multiply everything by 2. Just make sure you still write him as a linear combination. Now, if your brain doesn't like this guy, could you rewrite it in components, double it, and then rewrite it again? I guess. It might be nicer just to get used to the i's and j's and say, oh, no big deal, double them and double them, done. What if I'm adding? Combine like terms. U plus v, wouldn't it be 1i plus 3i? Could we line them up, make them look pretty? I suppose. But just combine like terms, 1i and 3i is. And then 5j minus 2j or plus a negative 2j will be 3j. Once again, if you don't like the linear combination, you could rewrite your vectors in those components that we worked with earlier. And you could, in a sense, do your math and say, okay, so you double them. Okay, 6, negative 4, and then write them in a linear combination form. You could do 1 plus 3 is 4, 5 minus 2 is 3, and then rewrite them. That works too. But we're also going to review right here the end class. Unit vector. Ooh, that was a thing. Unit vector. We're doing it on the board. You guys actually kind of just discovered what it was. Let's just do it in components, then we'll rewrite it. Who am I doing a unit vector of? Okay, and he already has 1 and 5, right? Do you remember how or why I'm drawing the division sign? I need to divide by the magnitude of u, remember? And the magnitude of u, even if it's given in this form, I can still say, well, the coefficient's 1 and 5, so I'll do 1 squared plus 5 squared, which ends up being root 26. And remember, you divide each of those. But if I was writing it in, well, unit vector of u, that's kind of awkward, but linear combination form, I would just rationalize to make it pretty. And I would put my I, rationalize to make it pretty, and put my j. Process is still the same, I just have opposites. Okay, it was with that, we've gotten up to, oh, we missed one formula. Okay, we're close. We have our word problems tomorrow. So you guys are allowed to stop just a little bit early in homework. You can stop at direction angles. If you get to a part where it says something about finding angles, you could stop, although technically you just need tangent inverse. Solving it right now. Alright, okay, it's final day of vectors tomorrow. I'm getting into word problems. I probably, no, I will. Spot check on everything up till the direction angle. Bye, guys.